All right. Good afternoon, ladies and gentlemen, our dear students. So, what are we gonna do today? We will talk about two things. Okay, volumes using cylindrical shells and the arc length. About areas of surface of revolution. Maybe I will share one video. It's about derivation of this formula. And tomorrow we will do some questions related to areas of surface of revolution and work and fluid force. And next week I will see, okay, moments and center of mass. Maybe I will just skip this at least for now. Later we'll talk about this, or because we are running out of time and 1 week is left, just only next week. And next week we'll talk about chapter 7. Okay, chapter 7, I think it is integration techniques. And after that, your final exam, you need to prepare for chapter 5, 6, and 7. Okay. After the Khmer New Year, you will have final exam. So yesterday we talked about volumes using cross sections, and today we'll talk about in this class volumes using cylindrical shells. Okay. So here we know that actually this volumes using cross sections, sometimes our cross sections in X, okay, it may not be an easy function to integrate, okay. So that's why in this kind of situations now we are going to develop another methods, okay, so that maybe it may help us to solve the problem much faster or in easier way. Because naturally in math, actually, if there's a problem, and naturally people tend to solve the problem using different methods. And actually this tendency makes a lot of contribution to the development of science or anything. Otherwise, if everybody does the same thing and everybody likes the same thing, there will not be much improvement. Okay, everybody wants to do something different from others. That actually makes things develop or improve. So let's just start this with this example. Okay, so what are we going to do here is we are just going to consider another case. Okay, and our purpose again, we are going to find a volume of a solid which is generated by revolving some kind of region around either x-axis or y-axis or any line. Any line means any horizontal or vertical line. Suppose that actually we are given this region, the region enclosed by the x-axis and the parabola f of x is equal to 3x minus x squared is revolved above the vertical line x equals -1. As I say in the first picture, we are talking about this red line, right? And around this red line, not y-axis. We are just revolving this blue shaded region around this red line. Okay. At this time, you will just see the picture in the second one. We will get this kind of solid, right? Now it is cross-section area, right? If you just find this, it's really complicated because if you find the radius of the circle, that means that you need to find this x. You need to solve this for y, x plus x in terms of y, and after that use this, it will be very complicated because what will be the radius here? The radius will be x, right? That x is in terms of y. Anyway, you can just try this. It will be very complicated. You can just try to solve this problem using cross sections. Anyway, instead, okay, we are going to do something else here. So suppose that we are going to find the volume of this, okay, and suppose in our hands we have a lot of different sizes of, let's say, like a cookie cutter. Okay, we just call this cookie cutter. Cookie cutter, maybe ladies know this. For example, if you want to make a cookie of different shapes, right, like say moon shape or heart shape or diamond shape, and then we have a kind of cookie cutter. You just press this over the dough, right, and then we just give different shapes to our cookies. It is something like this, okay? We have a different sizes and we just actually, how to say, with cookie cutter, I can divide actually with this solid into smaller cylindrical, let's say figures. See this even in orange. So when I just actually cut with two different cookie cutters, right? As you see here, I have a kind of cylinder here. So it is thickness. The thickness here is, what is this? I'm just talking one of them here. I'm just talking this orange area. As you see here, the thickness, what is the thickness? The thickness is, it is delta x sub k. right? Because here I'm just cutting from here, and after that from here and from here and from here. I'm just talking about one of them here. So that one is delta x sub k. Okay, so delta x sub k. So now I am going to approximate actually this the volume of one cylinder. All right. If you look in the first figure, what is the wall actually the height of this? For example, let's talk about one of them here, right? And to find the volume of the height of the cylinder, suppose that I just pick any point between from the interval delta x. I mean, whose length is delta x sub k? That will be what is it? F of c of k, right? So now if you just unroll this, I will get this kind of shape here in the second one. And if you just flatten this on the table, I will have this kind of slab. And you see here the thickness, it is delta x sub k. And because it was a cylinder, if you just unroll this, the length of this rectangle will be the circumference, right? The circumference of the base circle, that is 2 pi times r. And what is the radius here? The radius is x sub k plus 1. And you see here, this one is the radius. If you just pick any point here, it is a radius. And we know that on the x-axis, how do you find the distance between 2 points? Let's say if this one is -1, and this point is, let's say, this c sub k or x sub k, it doesn't matter. So what is the distance between these 2 points? The distance is, let's say, this d is equal to x sub k minus 1, which is equal to x sub k plus 1, which is it actually? That is the radius of the cylinder. So that's why here we have x sub k plus 1. Okay, this was 1 plus x sub k, that's the radius. And how about the height? Height is the value of the function at that point, right? Because our function is 3x minus x squared, right? That is the value of the function gives the height of the cylinder. And after that, we know how to find the volume, right? What is the volume of this one? The volume of this slab is equal to length times width times height, right? That's equal to length times what is it? Width times height. And what is the length here? Length is the circumference of the base circle because it is obtained by revolving about the that line. So now if you just substitute the values here, then the circumference, it is 2 pi times 1 plus this r x k. And how about the height? Height is the value of the function at that point, 3x sub k minus x sub k squared times width, it is delta x sub k, right? So now if you want to, what is it, find the volume of this, then I'm just summing up all of these volumes of the cylinders of different sizes. So here we have V1, V2, V3, because I divided this into, what is it, in cylinders whose width is very, very thin. Okay, and if you just add them up together, right, the sigma k equals 1 to n delta vk, that's equal to k equals 1 to n. What is delta delta vk? That's equal to 2 pi times 1 plus x sub k times blah blah blah. That's given in the above expression. So now we assume that as we just increase the number of these partitions, right? That means that if our cylinder's width gets thinner and thinner and thinner, that means that it gives us better and better approximation of the volume of the solid. And when n goes to infinity, actually it gives us the volume of the solid. So as see here, when n goes to infinity, what does it mean? It means that this x is assuming every point of the function over the interval. So that means that this, when limit goes to, I mean, the n goes to infinity, this x sub k is taking every point, which is just x, which is changing from a to b. And that's our function. So actually it takes the form of this integral, right? Simply this integral from 0 to 3, because here we have some kind of function times delta x sub k. It's our Riemann sum, right? 2 pi times x plus 1, 3x minus x squared dx. Okay. So now we know how to calculate this. If you just evaluate this first, I need to take 2 pi out and expand this x plus 1 times 3x minus x squared. That's equal to 2x squared plus 3x minus x cubed. That's just simple thing. You know how to do that. And also it's just a polynomial function. You know how to integrate and integrate this, get the answer. Okay, so using this method to find the volume of a solid which is generated or obtained by revolving about a certain horizontal line or vertical line, it is called shell method. Why? Because actually we are approximating the volumes by some kind of shells. And how we are obtaining shells? By using some kind of cookie cutters. So the volume of the solid generated by revolving the region between the x-axis and the graph of the continuous function y equals f of x, uh, where that's L is less than or equal to A, that's less than or equal to X, and less than or equal to B. About the vertical line X equals L is, what is it, 2 pi times shell radius. It gives us the length of the circumference times shell height. We're just finding, what is it, the volume of the slab, right? So dx. Anyway, that's another method. Okay, so let's just solve one question about this. For example, example 2. Okay, the region. Y is 2 and 3. The region bounded by 1, 1. Find the volume of the solid. Okay, let me just solve it here. So the region bounded by the curve y equals square root of x, the x-axis, and the line x equals 4 is revolved about the x-axis to generate a solid. Find the volume of the solid. This question, we have done this earlier. Maybe we did this yesterday using the cross-section area. Just here, we are going to use different method to do this. Okay, for some functions, you will see that shell method is good, but for some functions, it does not matter which method you use. Which one is easy for you, you can use that method. Okay, by using this shell method, and suppose that if you just revolve this region, as you see here, between the y equals square root of x, that is our that blue graph, right, and the x is equal to 4, that is red line, the vertical line, and also, okay, that's it. So we are just revolving this about the x-axis. So now I am just dividing this into smaller cylindrical shells. Okay. So if you just do this orange area, this red line, what is it? It just gives us the height of the function, right? And how about it is radius? As you see here, this one is the radius of the, what is it? Shell radius. This one is the shell radius, right? Because it is revolving about the x-axis, right? So from here, what is the shell height? The shell height is 4 minus this point, right? And what are the coordinates of this red point? And it is on the function y is equal to x-axis. When it is x, y value is square root of x, right? Or simply square root of y, square root of x. So if you just find the difference again, it gives us the shell height. So what is shell height? Shell height is equal to x2 minus x1. What is x2? Actually, it is 4. It's not changing. That's equal to 4 minus, and how about this one? That's equal to square root of x. But in terms of y, that's equal to, from here, what is x? X is equal to y squared. So that's equal to y squared, right? Because it is width, as you see here, the width of the cylinder, it is delta y, right? And y is changing from 0 to 2. And how about the width? It is delta y. Let's say width is equal to delta y, which is equal to, simply, it is dy. Okay. Now, how about the radius? As you see here, this is the radius, right? The radius is the height, that's y. Okay. So the shell radius, let's say the shell radius is equal to y, the height. Okay. So at the time, the volume of this one will be equal to, what is the volume? Volume is equal to integral, and y is changing from 0 to 2, from 0 to 2, right? Because we are revolving this about the x-axis, not y-axis. And here we have 2 pi, and here we have shell radius, that's equal to y, and shell height, that's equal to 4 minus y squared. And here we have dy. So that gives us the volume of this solid. So which is equal to, here we have 2 pi integral from 0 to 2. Here we have 4y minus y cubed. And here we have dy. That's equal to 2 pi. The first one is, what is it? It is 4 over 2. It's just 2y squared. Okay, here we have 2y squared minus the second one is 1 over 4y to the power of 4, and y is changing from 0 to 2. So when it is 0, it is 0 because every term contains y. When it is 2, here we have 2 times 4, that's equal to 8. minus 2 to the power of 4, it is 16. 16 is divided by 4, that's equal to 4, which is equal to 8 pi units cube. Okay. All right. And also, if you remember, for example, this cross-section area, that is just our shell method. And by cross-section, how do we calculate this? If you remember, that's just equal to that volume is equal to integral x is changing from 0 to 4. That here we have pi times r squared, right? And what is r? R is square root of x, right? Square root of x squared, that's equal to x. And here we have dx. That's equal to pi times 1 over 2 x squared integral changing from 0 to 4, which is equal to 8 pi, the same answer. Okay, I'll say here cross section of core method is much easier and faster, but here we are just using another method because for is in the first example, for example, y equals 3x minus x squared. If you try to use this cross section area, it is more complicated than shell method. So depending on the problem, which one actually gives us the solution faster, we can use that method and get the question solved. So regardless of the position of the axis of revolution, horizontal or vertical, the steps for implementing the shell method are these. Draw the region and sketch a line segment across its parallel to the axis of revolution. Label the segment's height or length, shell height, and distance from the axis of revolution. Shall already find the limits of integration. Anyway, and these are just the method what we have done, okay? As you know here, first, the most important thing is you need to draw the region. And after you revolve this, what does it look like? Okay, you should be able to visualize this. And if you just cut it with some kind of, let's say, cookie cutter, for example, what will be the length of the cylinder and the width? And after that, it is a radius, right? Because to find the volume of the shell, right, we need to unroll this, just flatten this and put it on the table. So it becomes like, what is that? Cuboid, right? To find the volume of the cuboid, we need to know its length and the width and the height. And after that, we can get. Sure. Okay, that's all about this first part of this chapter. Now I will continue, but let me just give you 5-minute break, okay? Because I don't want to continue from here. And in the next session, we'll talk about arc length. And that's it for today. You need to practice questions, and tomorrow we will continue, okay? Like exactly 10-minute break. After 10 minutes, we'll get back to the class.